Hi there. So this video is just going to be sort of like an add-on to the video about Suvat equations and mechanics, mainly just because the Suvat equations are going to be the main equations that you're going to be using in order to discover and calculate all of the different points of projectile motion. So Suvat equations are really all that you're going to need. And one thing that you'll notice is that these Suvat equations have nothing about angles in them. And this is a very important reason that I will explain in 1 second. But just as a little precursor, so projectile motion really just refers to any time that something is given force and it causes it to fly through the air and then land, hence making it a projectile. So there are two main types of starting forces, or initial forces, as I like to call them, which will create projectile motion. So the first one would be completely horizontal force, and this can only really be done if there's something on an elevated height, because otherwise it's just going to be skidding along flat land. So most of the time you'll see something being kicked directly straight off of a cliff or rolling off of a table or something like that. The other type is going to be parabolic motion, and this is usually created by an angled force at the very beginning, or initial angled force. So when you kick a soccer ball or something, you'll notice that you kick it up at an angle instead of this, where you would be kicking it or pushing it directly straight. So when projectile motion occurs, you'll notice that there's direction and movement in both the x and the y-axis, right here. And the best way that I have found to be able to conceptualize and work with projectile motion, not even using the equations, but really just thinking about it, is to separate the motion into its component parts of motion in the x direction and motion in the x direction and motion in the y direction. So if a great way to really think about it and think about splitting this up into its integral parts would be to imagine that you're looking at this ball through a slit. And so imagine it gets kicked off of this table, right? Or cliff, or whatever it wants to be. Imagine it's kicked off and you can only see the ball, right, through this slit. And also imagine if this slit covered up the entire paper and you couldn't tell whether the ball was moving left or right or at all, really. All you could tell would be the ball's direction or the ball's position in the y coordinates. So all you could really see for this one would be that the ball is staying still and then it slowly falls. Similar, if you were to look at the motion of this ball, which is a projectile, you would see that the ball, if it was looking through the slit, would only really just go up and back down. And we could see that right here, right? So it goes up and it goes back down. And now imagine if you didn't know, the best way to think about it would be if you did not know that the slit was moving, right? So all you saw would be what is inside of the slit. So another way you can also do that would be with the x direction. And you notice with here, it moves forward, it moves forward, it moves forward. Similar here, it just keeps moving forward, right? So with projectile motion, right, if you split it up, all it really is doing is just dropping as well as moving forward at a constant speed. And this one is just lifting up and falling back down at the same time as it's moving at a constant speed. And now you can understand why Suvat equations actually don't have angles involved in them at all, because it doesn't matter what the initial angle of this kick is. All what really matters is how much has it been kicked in the y direction and how much has it been kicked in the x direction, and then you can use the Suvat equations. So while that's all fine and good, that really still doesn't tell you much, right? Because this is still very conceptual. So what I'd like to do is sort of explain to you one very, very important concept which will really help you in the long run with a lot of projectile motion. And that is that what you'll see is that whether you were to kick this ball off, whether you were to shoot a bullet out, or whether you were to just drop a penny, imagining that all of these scenarios happened within a vacuum, they would all land at the same time. And the reason for that is that the x velocity does not change the entire time, because the only way for this velocity to change would be if there's a force acting on it, right? So normally we see this force as air resistance. However, in physics, especially in the beginning, you're not going to be calculating with air resistance. So if this were to be done in a vacuum, you kick this ball off at 5 meters per second, it lands here with 5 meters per second. You kick this ball up and the x amount of force is 5 meters per second, it will land with 5 meters per second forward of force. So when you're calculating this, the only thing that is really changing, the only velocity that's really changing, is the one in the y direction. And that's because gravity is always acting on it. So right here, you can notice the only thing that's going to be changing is just that the y values are going to slow down. So that's a bit abstract at the moment, right? And I'll explain that further in detail down below. But one way that you can also put more concrete ideas in this is that, so okay, so let's say that we're going to be taking a look at this parabolic equation right here. Now, let's say that someone were to kick this ball at 5 meters per second. All right, so here's the thing about projectile motion. This diagonal arrow does us no good. What we want to find is the arrow in the y direction and the arrow in the x direction. And right now this might seem still a bit abstract. You can't infer much from this. You know, you still have one arrow, but all you have is just two arrows that are the same height or length as it. So what do we do here? Well, if you remember some trigonometry, we can actually just move that line that used to be over here, right over here. And it leaves us with a perfect right triangle. So now we have a right triangle with the hypotenuse of 5. And we'll know that this one, or yes, we know that this will be a 3, 4, 5 triangle. So you know that it is imparted with a 4 meters per second to the right and 3 meters per second upwards. And that's all that you're going to have to worry about. And the best part about parabolic motion is that whatever you start with, whatever forces you begin with, so say 3 meters and 4 meters per second, that's going to be the exact same thing that you're going to end with. And that's just because, due to the nature of a parabola, and since it is symmetrical, and since gravity gravity takes as much time to slow it down as it will to speed it back up, it's going to have the same amount of speed when it hits the bottom. So, like I said, at the bottom, or at the end of the parabola, let's draw that out. We're still going to have a 5 up here, and we're still going to have a 3 right here. The only difference is that this 3 is now -3 meters per second. All right? And that's just because that's due to the nature of anything that you'll throw up or shoot off. As long as there's no difference in from where it starts and where it ends, as long as it's a completely flat surface, the beginning velocity upwards is going to be the same as the final velocity downwards. And like I said, the x value will not change. This 4 meters per second, it's still 4 meters per second. And that's just because there's nothing affecting it in the x direction. There's no force pushing on it, right? If there was wind pushing on it, this would change. This would be, maybe 2 meters per second if there was a big gust of wind. But if there's not, we're treating this as if it were in a vacuum. So this 4 meters per second that it begins with is the same 4 meters per second that it ends with. With this same idea, that is the same idea that allows us to make the inference that the speed of the initial, trajectory, or, the initial speed that this object over here would be pushed off at has no bearing on how long it takes to hit the ground, right? So that is also why a bullet and a dropped object will land at the same time. And that's just because it doesn't change and there's no effect on the y value. And the y value is all that really affects how long it takes to hit the ground, right? Because if you were to, throw something upwards, of course it would take longer to hit the ground. But if you're just dropping something, right, as compared to dropping something with a big speed as attached to it in the x direction, these arrows don't change. These arrows are going to be the same, right? The force down by gravity affects both of them equally. The only thing that the direction that the amount of force that is given in the x direction will change is how far it goes. So that's why one of them will land right at the bottom and one of them will land 300 feet away. So the x value, most of the time, is much less important than the y value of the initial velocity that is given. So I'm going to pull this away. Now I'm going to show you these. And if I were to show you these at the beginning, this would be much more confusing, but hopefully now you'll have somewhat of a better understanding of it. All I really did was graph the velocities of the x and y values at any given point. So, or at most of these points. So you can see throughout the whole time that all of these arrows in the x direction are the same length or as similar as I was able to draw them. However, the arrows in the y direction slowly increase in their value. And that's just because there's no force pushing back on it, but there is a force pulling down on the ball, and that's the reason that it drops. So you can see it slowly increases velocity downwards until it hits the ground. And then in a parabola, it's a bit more confusing, but actually, let me bring this paper back over here. If you cut off the bottom half, or the first half, you'll notice it's the exact same up here, right? There's just the same thing going on. So all there really is just, another half attached to it. And you can see that the length of this arrow at the very beginning going upwards is going to be the same length as this arrow going downwards on the opposite side. The only difference is that they're just in the opposite direction. Similar to how 4 meters per second is the same value, 3 meters per second is the same value as absolute value as negative 3 meters per second, but all the only difference is that they're in opposite directions. One's positive and one's negative. So we come back here and you can much more easily conceptualize that the only real thing that's going on is that this ball is being thrown upwards and it's landing downwards. Attached to this is going to be a speed in the x direction, which just pushes it forward as it's being thrown up and down. So when you learn to separate all of these motions into just, two things happening at the same time, it being thrown and it being just moved, you can get a much better understanding of what is going on. So another possible thing that would happen would be, okay, let's say that, let's go back to this idea right here. So let's say the ball is thrown at 5 meters per second upwards, and it wants to know how long is this going to take to hit the bottom again? How long is it going to take to hit the ground? What you can all just do is, first of all, we're going to find the y value, all right? So 3 meters per second. So now that we know that the x value really doesn't have a bearing on how long it'll take, all we have to worry about is, let's say I threw a ball, upwards with 3 meters per second. How long will this take to hit the ground? Now we can bring in our Suvat equations. And with Suvat, or at least with this idea right here, we still have sort of a complicated thing going on because we have, it's going up, but then it's going to, right after it goes to 0, it's going to go back down. So what do? Because our initial speed, going back to our Suvat ideas of, let me just actually write them down right here. So we have S, we have U, V, A and T. All right. I'm going to keep my Suvat equations off to the side, but I'll bring them back when I actually plug it in. So first, we're just going to get started with plugging in our variables. So we immediately come to an issue when we start with the S, with the displacement, because, it's a parabola. So is our displacement going to be in the x direction? Well, no, because we've already disregarded the x, because we know that the x is not going to affect the time. Okay, well, so then the displacement has to be 0, right? Because it goes up and it lands and it doesn't actually move then, because we're not using the x. Not really that either, because if you were to do that, it doesn't help us. Because if s is 0, then, this entire equation is equal to 0. So that's not going to help us either. So what we have to do when we're Suvating with a parabola, especially an equation where it goes up and then back down, what you really have to do is actually, well, what if we only just take this part of the side? What if we just take that part of the entire thing that's going on? So now we've taken this entire big curvy parabola and this ball that's traveling really weird and all these curves and everything, and all we've simplified it to is, all right, well, how long is this ball going to take? If we throw this upwards, how long is it going to take to stop? Because we know that the amount of time it takes to reach the top is going to be the same amount of time that it takes to reach the bottom. So all that we really have to find out is, well, how long does it take for its velocity of 3 meters per second that has been given to go to 0? Because every object, when it goes to the top of its parabola, will have 0 meters per second as its speed, because there's nowhere else for it to go. The gravity has completely taken out all of the velocity. So then from there, it can turn around and, come back down to the Earth. But all we really need to worry about is just 3 to 0. So we've simplified this whole thing very much just by really thinking about how the different x and y's interact with it. All right, so let's continue then. So we're going to say the s is still unknown. All we know is that it's been shot up at 3 meters per second. So we're going to keep that as a question mark. Initial speed, great, we know that. It's going to be 3 meters per second. V, final speed. All right, well, we know that. It's going to be 0 meters per second. Acceleration, we do know that because this is on Earth. It's going to be negative, let's use 10 for this one because we're just going to keep it simple. Negative 10 meters per second. And then the time is what we're trying to find here. The time is going to be our x. So right now, let's pull back our Suvat equations and let's take a look at what's going on here. All right, which one has t as an x? And that would be this one. However, there's a big s in there. That's going to be our displacement. We still don't have that, so we're going to have to find something else. All right, well, this one has v equals u plus at, but s is going to be a variable here, the t is going to be a variable in there as well, which we don't have. So what we're going to have to do is we're going to have to do a little bit of messing around with these equations. Since we have two unknowns, we're going to have to kind of set some equal to each other. So I'll give you a bit of time and try and figure out what that's going to be, and then we'll come back.